All right, let's do some more examples. And for this examples video, I'd really recommend you pause the video when I introduce a problem and see if you can do it on your own before checking my answer. It's good practice to be able to figure something out first and then go over it together to see what you got, what you missed, some things that you may have thought about, some things may not have thought about. So that is my recommendation for this video. Not a lot of new stuff, just kind of reiterating with some more examples, the stuff from the last video. So let's say we're looking at Washington license plates, which as far as my research led me, is always 3 letters followed by 4 digits, excluding personalized plates, which we'll talk about in letter B. Okay, so if we have 3 letters followed by 3 digits, how many license plate combinations are there? Well, there are 26 letters of the alphabet. There's no upper or lower case. It's all just uppercase as far as I'm aware in license plates. So, yeah, there's going to be 26 options for the first character, 26 options for the second character, 26 options for the third character. I think they can all be the same letter, but if they can't be the same letter, this would be 25 and this would be 24. We'll talk more about that in a future section. But if hypothetically they could be all the same characters, I'm not super familiar with Washington license plate conventions. And then of course we'd have 4 digits. Each digit can presumably be the same number. So there's 10 for each. So the answer is just 26 cubed times 10 to the 4th, which if we type that into a calculator is going to be a pretty big number. 26 cubed times 10 to the 4th. Shout out to Desmos. Okay, that's about 175 million. 175,760,000. A little bit more than the Washington state population of 8 million people. So we are pretty good with possible license plate combinations. And if we extend this to allow personalized plates, any combination of letters and numbers and any length between 1 and 7, this becomes a more complicated question. We have to break this question down. Okay. We're going to need to look at all the license plates of length 1, all the license plates of length 2, all the license plates of length 3, because again, personalized plates don't need to have 7 characters anymore, as far as I'm aware. Again, disclaimer of I'm not super familiar with the Department of Transportation requirements for personalized plates. I've never had one. But going off this example from the book, if you can theoretically have any personalized plate here, what is it going to be? Well, again, the total is just going to be the total for all length 1 plus the total for all length 2, all the way up to the total for all length 7. So if you only have 1 length, well, you have 26 characters and 10 digits. You can have 36 things on a single character personalized plate. I don't think they allow this, but I'm not quite sure. 2 is going to be very similar, right? You could have 36 for the first character, and you have 36 options for the second character. Again, following this assumption. Is this assumption correct? Who knows? But following the assumption, this is how you would do the math problem. And you would go on, right? This is just going to be 36 cubed, and then 36 to the 4th power, etc. And so what you could do, we could kind of do a little shorthand here. This would be the sum. What's the pattern here? 36 to the 1st power, 36 to the 2nd power, 36 to the 3rd power, all the way up to 36 to the 7th power. We're just adding up all the 36 to some power, and those powers start at 1, and those powers go up to 7. So again, you don't have to use this notation, and I haven't formally introduced it, but it is a good shorthand notation. So we're adding up all the powers of 36 between 1 and 7. What would that look like? 36 to the 1st power, plus 36 to the 2nd power, plus 36 cubed, plus 36 to the 4th, plus 36 to the 5th, plus 36 to the 6th, plus 36 to the 7th. And we have a pretty big number. I'm pretty sure Desmos actually does. Yeah. From 1 to 7. Desmos also lets you do it this way. You could change this to eyes, I believe, if you wanted. Da, 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 da. And you can see it's the same thing. This is a little easier to write, but these mean the same thing. So a very, very big number. What is that? Like 80 million or something? Or is it billion? I'd have to count. It's a lot. I think it's 80 billion. All right. So 8.060 times 10 to the 10th power. And let's say that we're approximating this. I already forgot it. 8.060 times 10 to the 10th power. And let's just see, right? This is going to be times 10 to the first power, second, third, fourth, fifth, sixth, seventh, eighth, ninth. Oops. 10th. All right. Bad commas. But yeah, it's 80 billion. It's a big number. Roughly 10 times the population of the world. Lots of options. All right, let's continue this little practice. This next example, part A, is going to be very similar. But what I challenge you is, what do you think is going to be bigger? Before we even answer this question, what do you think is going to be bigger? All the passwords of length 6 through 10, or just the passwords of length 11? Let's find out. So just like before, right? A quick comment over here. The only reason we can add these up is that these are mutually exclusive, right? These are disjoint. If you have a password of length 1, it is not a password of length 2. If you're adding up things that are not mutually exclusive, you have to subtract out the duplicates. You have to be very, very careful. Anytime you're adding up a bunch of combinations or a bunch of people or a bunch of things, you can only split it up like this if it's only possible for everything to go into one thing. If we have some kind of partition, maybe that would work. So be very careful. So similarly, right, if you have a 6-character password, it's not a 7-character password. The 7 characters could have the same first 6 characters, but they're different passwords. All right. So similarly, we're going to add these up. We're going to have to find out all the 6-character passwords. Well, alphanumeric, that's going to be 26 lowercase, 26 uppercase, and then 10 digits. So that's going to be 62 options. So again, if there's any combination, well, it's going to be 62 for the first, 62 for the second, 62 for the third. It's okay to have a password of A. Yeah, that was 6. Great. Not a great password, but it is a valid password here. We'll introduce more restrictions in the next video. But yeah, it's just that times itself 6 times. And then again, very similarly, right, to do 7 characters or 8 characters, we're going to get it. So the total is very similarly, we're just adding up from 6 up to 10 of those n sub i's, which is just 62 raised to the ith power. And again, if you don't want to use this notation, that's fine. It's just 62 to the 6th, plus 62 to the 7th, plus 62 to the 8th, plus 62 to the 9th, plus 62 to the 10th. These are how many possible passwords there are of each length. And again, you add that up. Let's go from 6. I'm going to use a shorthand to save myself some time. Oh, let's not write it like that. 6 to 10 of 62 to the ith power. And let's make sure I typed it in right. We are getting some big numbers. Combinatorics often leads to very big numbers. Ooh, I just realized I had a little chuckle here, a little inside joke. We'll see this later. When I wrote counting, I wrote an exclamation point. Exclamation points are going to come into play in this chapter. You may have seen exclamation points mathematically before. But yeah, I put that there on purpose. Hopefully you saw that. Hopefully you noticed that. Anyway, a little Easter egg for you. What's the answer? It's 62 to the ith power from 6 to 10. 8.531 times 10 to the 17th power. That's a big number. Lots of possible passwords. If you're trying to guess a password and it's a randomly generated password, which again, that is not the case for most people's passwords, but it is becoming more common than it used to be anyway. But yeah, if you just going through all the lists, all right, let's do AAAAA. Let's do AAAAB, AAAAC, right? If you're going through all this, you're going to be there for a while. It's going to take a bit of time to go through all these passwords. I would recommend starting with the guess password. But anyway, that's how many there are. I'm not going to write out this number. It's a big number. It's a lot of zeros. Well, a lot of not zeros, actually. But if we approximated it, it'd be a lot of zeros. Okay, let's see which one's bigger. 11 characters. That's just going to be 62 to the 11th power. What's that? Go to the calculator. 62 to the 11th power. 10 to the 19th. Oh my gosh. 5.204 times 10 to the 19th. These things grow exponentially. So even though we're adding up a whole bunch of different lengths of passwords, as soon as we add another character to this password, it just gets so much bigger that it doesn't matter that we're adding up multiple lengths here. Adding another digit, adding more options, these make things grow exponentially. So yeah, this one's going to be bigger, and yep, lots of 11 character alphanumeric passwords. We don't even have special characters yet. Lots of options. Combinatorics deals with big numbers. Again, I'm writing my scientific notation with different multiple signs. Both are okay. All right, just showing that both ways of writing this are fine. I think for scientific notation, this one is more common, but you can write the dot if you're used to writing dots for multiplication. Let me know if you have questions, and hope you're ready to count some big numbers, because here we are in chapter 6.